TD-based. The second Lustre storage system we have at Stanford is Oak Storage. It's a global capacity-oriented Lustre file system. So we build it with large I/O cells. So the largest are currently 11 petabytes each. It's a rack. We maximize the number of disks versus the CPU. It's about 40 petabytes usable, but before the end of the year, it's going to be 51 petabytes usable at least. We have a lot of demand. And at this scale, it's very large for a university to have that much data on one namespace. We have a very strict inodes per volume ratio, so 150,000 inodes per TB. And that allows us to maintain control on the file system. And even though we have 2.1 billion inodes used right now, we still we avoid like crazy amount of inodes generated by user by mistake often. So that's a fact I wanted to mention. The other interesting fact is we are using QoS, so NRS-TBF per GID on the OST and OST-IO services. And we spend a lot of time finding the right settings for NRS, and we are quite happy with this setting now. We are setting rates limit per group, so basically per Oak space that we allocate. But the rate is in function of the space they purchased. So if a group have 1 petabyte, it will have more. It will be allowed to do more RPCs. And Oak is offered to our researchers as a service. And so it's not free, it's for a fee since 2017. And all this space, I mean, it has been very, very successful. They are very happy. So I made this diagram to summarize. At the top, you have the Lustre clients. At the bottom, the Lustre servers. So we have Sherlock on multiple IB fabric. We have the SCG cluster. We have also Oak gateways, because Oak, this big system I just mentioned, some groups want to access it directly via specific protocols, not from the cluster. And for example, SMB access is very popular. So we have those VMs that run on a KVM hypervisor farm, and we use a virtual function, so SRIOV, for that. So Oak gateways are also Lustre clients. And we also have a backup swarm. So we have like a pool of nodes managed by Docker Swarm to back up Oak to the cloud. It's not the default. You have to have a cloud account. And so some researchers have cloud credits, or sometimes they are scientifically obligated to back up their data to a remote area. In that case, we help them, and we orchestrate like the REST backup to the cloud. So clients at the top and server at the bottom, Fur and Oak. And the next slide, we reveal the Lustre version we are using on those systems. So we are still mostly using 2.12.9, but on Sherlock, we have completed the full upgrade of all Sherlock clients, so the 1500 Sherlock client to 2.15.0. And we have been happy with that. It has been quite smooth. So very happy about 2.15 clients so far. Next step will be to upgrade the servers. So that's it for the update. The next part of my presentation, there will be 2 parts. The first one will be, I will discuss how we manage the life cycle of hardware on Oak storage. And the second part will be how we plan to upgrade Fur, or Scratch file system. So Oak, Oak, it's like funded through a university service center. We don't have big central funding for that. So it's like constantly evolving storage system. And we have to answer the demand, right, and manage the systems. So basically what we do, the hardware lifecycle on Oak, it's basically 2 things. We add storage when we need to accommodate more demand or replace old storage, and we remove storage when the storage, the hardware is too old, or we reach the end of warranty, or we are not able to source any spare parts anymore. So it looks simple, right? We add and remove storage. Now the method we use for adding new storage, so we prepare new OSS, new OSTs, adding is easy. In Lustre, you mount new OSTs. We always use, in our case, we don't reuse OSTs, so it's important to mention that we are using always higher OST indexes. So when we add new storage to Oak, we use increasingly in OST indexes. The harder part is to remove the old storage. That's because Oak now is more than 5 years old, so we have started to remove, and we removed already old equipments, and so this problem came up. So we remove old storage basically in the recommended way by the Lustre manual. We set the OST in no create mode well in advance for the storage we want to remove, so that there won't be any recent files stored that. So when you set that on the MDT doesn't allocate new object on those OSTs. And then after sometimes we need to empty the OSTs we want to decommission. So we migrate data, and we do that with LFS find and LFS migrate. So recently I've been using LFS_migrate more because we also restripe files. We have some very large files and a number on Oak, so it's a good opportunity to use LFS_migrate. We have some nice options to set the striping in function of the size. This is because we didn't have PFL at the beginning. So most objects on most files that are located on the first OSTs are still using the legacy, plain layout. So it's important. I mean, it's a good opportunity to restripe them. And then we deactivate, when the OST are confirmed to be empty, we do a last check with LFS find. We deactivate the empty OSTs with LFS conf_param. And the next step is to permanently remove the OST from the file system. And for that, we use a new command that is lctl del OST, so for delete OST. And I will talk about it in just a moment. It's worth noting we are removing OST indexes from the lower indexes, and we are not reusing them. So basically, we have a sliding window of indexes over time. So I made this diagram to understand a little bit better. You can see at the left, we started with IOCL 1. We added 48 OST. Then, because we had I put the need of new IOCLs is driven by demand. So yeah, we have more researchers interested in storage. So we had a second IOCL, a third, a fourth, and five. So over time, at the beginning, we only had OSTs. But after some point, the warranty, you can see, after the first IOCL, the warranty was 4 years because of Quanta JBOD. We need to get rid of it. So we started to remove OST now while still adding more OSTs. So we have this game of removing, adding. Of course, the OST we add now are much more larger in capacity. In IOCL 8, it's like the equivalent of 3 or 4 times IOCL 1 in volume. But that's the big picture of the life cycle of Oak over time for the OSTs part. The warranty time may vary a little bit. You can see that lately we have been using Western Digital JBODs, which it's nice because they came with 5-year warranty, so it's slightly longer. That's it for the life cycle overview. So to come back on LCTL Del OST, it's actually a development we made in collaboration with WarmCloud, and Andreas, who is here, actually wrote a long time ago some specification in a JIRA ticket, the LU7668. But nobody was developing it. So we said, oh, we need that. Because Dell OST, what it's doing is like you can remove OST permanently without doing a write conf. So if you don't know what a write conf is, the normal way, or until now, the way to remove OST was to shut down everything, clients, servers, and you do a write conf by forgetting, the OST you want to remove. So you basically register all your targets again to the MGS, and that it's forgotten. But that's very, imagine we have to do that at each time we have to remove OST, that would not have worked. So Dell OST is a great alternative to that. We can do everything live. So thanks to Andreas for the help reviewing the patch, and it's landed on 2.16. And a backport is possible, but I wanted to mention that while testing, while using Dell OST in production, we hit a bug, because basically Dell OST will cancel record, in the config log of the MGS, and propagate this change to MDTs and clients, and we discovered there was a bug when those cancel records were propagated. And so Etienne Ojam, who is in this room, thank you, Etienne, helped for fixing that problem and fix this bug. But if you backport it, you need the patch for LU 15,000. And finally, a side note, Stanford Research Computing is going to has submitted a paper to the HPC CISPROS 2022 as supercomputing, and Dell OST is actually part, and it described it in this paper. So that I encourage you to check it out when it's out in November. That's the part. So now the last part is different than Oak. It's we need to upgrade for our Scratch file system. It's old. It has served its purpose. But we see, you have probably all seen like new kind of jobs, deep learning jobs, or we see also, we have a lot of cryo-EM, the cryo-electron microscopy, which work on very large data sets in a random I/O fashion. So it's time to have some flash on the OST side. And so we advocate for a flash upgrade on offer. So it's different than Oak, because this is more like we get a bucket of money to upgrade for. So the goal in this upgrade is first to increase IOPS, because all our OSTs are based on HDD today, and if the data set doesn't fit in the OSS cache, we have limited by the IOPS from the drive. The second goal is to increase the bandwidth, because we have seen a plateau of bandwidth because just HG100, we have server with HG100, we need more. And the volume also, we have more, the user base, our user base is growing, and researchers really don't want a retention period less than 90 days. And some have been very vocal about that. So even though, 90 days can seem long to some of us, they really are not ready to have less than that on Scratch. So we would like to keep 90 days as the retention period for the data on Scratch. But currently our Scratch is almost full. We are at OSTs are 95% on LDiskFS, it works well. So 3 goals, it's a lot to ask, but we are going to do that in an easy way. I think it's like to replace our current JBODs and server with SSDs. So nothing as fancy as the previous presentation about NVMe over Fabric for now. So let me present what we are going to do. We also limited in footprint, so we are going to do a live in-place upgrade. So FUR has 8 I/O cells. We are going to upgrade each I/O cells live without downtime. That's our goal. So we figured out a way to reuse the same footprints and we are going to remove the old HDD and put a new IOCL. So this is an example. So our project will use the Seagate Exos E platform. So basically it's a JBOD, a JBOF, and with SAS drives that are SSDs. And the goal is to use, like today, MD-RAID on top of that. So we'll see the challenges with that in terms of performance. But we also are going to upgrade the server, so we'll have HDR200, PCI Gen 4, and multiple SAS cards to have the back-end bandwidth. So the way, so we have the principle of minimal disruption, as I said. Users already have data on Scratch, and they don't have time to copy data to another file system or something like that. So our goal is to bring new performance by upgrading those IO cells step by step. The goal is to just, over time, end up with at least twice the performance, but without downtime, without disruption. So this has started, actually, because we just received the hardware for the first IO cell. So we have set the first IO cell in no create, and because this file system is purge, we just use the purge, and we wait 90 days. And this is a graph, a usage graph of OST 0. You can see we just wait, and those objects are deleted by the purge over 3 months. So when I'm back in the office, I have to see, because it's not fully at 0, so there must be some files remaining. Could be files that, the user keep writing to it. In that case, the data version changed, and the file is modified, and it's legit, it stays on the OST. It's not purged. So once we have emptied those IO cells, we will retire those IO cells, those OSTs, with Dell OSTs, of course, and replace so the hardware, the server and JBOD with the new hardware. And then we add the new IO cell to the file system, and we put the new OST in production. After some testing, there will be full flash, and we rinse and repeat for each IO cell. Ultimately, we'll have we expect a performance boost of course, bandwidth. IOPS will be hopefully magnitude higher than today, and also usable volume, because SSDs we are going to use like 15.36 TB SSDs, just more larger than the drive we had, the hard drive we had from 2018. So it looks like this is the first IO cell. So this is a view of the 2 racks of fur, and when we replace the first IO cell, it will look like this. And then we replace the second, replace the third, fourth. So, and we'll continue like that until the 8th, okay? And then in the end, we will end up with FUR 2.0 with full flash OSTs, and a total of 768 15 TB SSDs, and almost 10 PB of usable space. Now, we only have the budget for half for the next year, so we'll see if we can do that fully. But so we might have some period we will have a period with mixed SSDs and HDD. That's why the presentation yesterday about hot pools was very interesting to me. What are we going to do during that time? The best use of the storage during that time. But ultimately, we really want to have to not have to worry about tiering and migration, and have a full flash Scratch file system, which will accelerate all jobs basically on the cluster. So it's a win-win for everybody. And that's it for my presentation. Thank you. Any questions?
Any questions from Stefan?
How do you manage the fact that when you add new OST, they're empty, and then Lustre allocate everything on those few new OST compared to the file system, so you have maybe less bandwidth at this time?
You mean for FUR when I remove the ISL, or
whatever? When you add new OST to one file system, then most of the objects are going to be allocated on this new OST. So you have only few OST working, and then you have a problem about like the
Yes. That's
the
a very good
balance.
point, and that's might be an issue on Fur. On Oak, you know, we have NRS. It's not for high performance. It's like longer term storage, and we see definitely when we add new OST, and we try to add enough OSTs. Like usually, we try to add a full rack to add enough OSTs so that they can handle the load. But definitely, Lustre will use them first, you know.
Yeah,
And we
then you don't try to force a bit the rebalance of the file system.
So on Fur, that's on Oak, we know it works because it's not like a heavy-duty file system. But on Fur, when we are going to put this new IO cell in production that has empty OSTs, of course, all the workload will go there. So it will be full flash versus HDD, so might be able to, maybe it's a good stress test for it, but it will fill up very, very quickly. So
yeah, because the risk is that the user will have not the same experience every time they use it, depending on the OST.
Yeah. So they are tunable for, we could...
Yeah, but it's pain for the admin.
Yeah. But we might have to look at this and see if we can disable, you know, the space, smart space allocation for Lustre for a while, or to force a round-robin allocation instead. Yeah. Very good point.
Good luck.
Any other question?
What about the MDTs?
Yeah, it's a good point. This presentation, as you have noticed, only cover the OSTs. The MDTs, I'm waiting for OneCloud to land the FLR for MDT, like in 2018. Because that would be great for upgrading MDT, you know? You copy your MDT and then you get rid of your old hardware. But today, it's difficult. We don't have a magic solution to do that without a downtime.
You can do it if you have LVM, you can, sorry. Yeah, if you have LVM, you can use that to migrate the storage underneath the MDT essentially, and then, you know, I've done that at home, granted not very high load, but you know, use PV move, and then you can replace the storage without taking the downtime. You'd still have to have the, you know, the node is not going to be replaced, right?
And all MDTs are quite large. On Fur, they were designed for DOM, so they are like 10 TB MDTs. So it's a challenge. Yep.
You have quite dissimilarly sized OSTs.
On Oak, yes.
Yeah. Do you experience any performance degradation as a result of that
No.
quite notably dissimilar size?
No. Again, Oak is not like or Scratch. It's like it's not the high performance file system. We found out that Lustre is making very good use of unbalanced OST size. The first OST has 64 TB. You know, our latest is like 192, I think, TB. And even though the OST size is different, Lustre does a good job at managing that in a good way.
You don't suffer bottlenecks on the node network side because you've got vastly
haven't
different
noticed that.
allocations.
Yeah.
No, okay.
But it's something that could happen with Fur because the OSTs, OST flash will be bigger. But they will be flash, so flash-based. So
yeah, your bottleneck's in a different place.
yeah.
Last question? Nobody? Okay. Thank you, Stéphane.
Thank you.
So welcome to Sebastian Pursky.
So our next presenter is Sebastian Pursky. He's been working on Lustre since 2005. After spending 10 years at level 3 system support engineer at Pulatos, He's now a storage and I/O performance advisor, performing I/O benchmarks and architecture for pre-sale.
So, hey everyone. Today I'm here to present you a work about Lustre in an LNet rooted environment. This talk was inspired by an installation which was performed at ECMWF the last year. And so I would like to give a bit of context before going into the technical details. So ECMWF is the European Center for Medium Range Weather Forecast. So as its name implies, they are doing forecasting, and for this they rely on a lot of input data and parameters, as you can see, which are collected about all that happens on land, ocean, atmosphere, and things like that. That means that they need to process a lot of data, and for this they need a large computation facility. So for this we provided them last year in their brand new center in Bologna, Italy, some clusters based on our Sequana XH2000. So you can see the center here. The facility is composed mainly of 2 data halls, so that you can see here. If we, okay, and so those are actually divided into what are called 4 complexes, where each complex is actually including 2 clusters. So one cluster is based on the XH2000, where the nodes are grouped in cells of 4 racks. So there are 5 cells per cluster, and this means there are about 2,000 nodes per cluster. There are 4 complexes divided across the 2 data halls, and so we get in the end about 8,000 nodes aggregated. On the storage subsystem, everything is based on DDN appliances. There are 10 independent exascalar systems, again, which are divided across both data halls. And so you get 2 types of file systems. One is called time critical, which is for production, day-to-day production. And the other file systems are for research. In the time-critical storage, you have 2 file systems which are 700 terabytes based on flash, and 2 other file systems based on HDD with a 5 petabytes capacity. So all the file systems are accessible from all complexes. Each complex, so as I told, is composed of about 2,000 nodes. You can get different specs here, but the main interesting factor is that we get 2,000 nodes and in total 8,000. This is about the specs of the file systems. So the flash-based file systems are 700 terabytes and able to sustain about 300 gigabytes per second. And the HDD-based are 5 petabytes and able to sustain more than 100 gigabytes per second. Then comes the file systems for the research, which are 13 petabytes and able to sustain 260 gigabytes per second. So here you can see the way the complexes are laid out. So you have the two halls. In each hall, you have 2 complexes, and all complexes will access both data hall storage fabrics through 30 LNet routers each. So you can see that already there is quite a proportion in the number of nodes against the number of routers, which is a part of why I'm giving this talk. So before explaining what kind of troubles we could have seen, I would like to remind a bit of theory about LNet routing. So a part of the information I'm going to give is from source browsing, and some parts are also assumptions. The source was based on the 2.12 version, so some things might be outdated, some others might be incomplete, but I guess a lot of people here could correct me if I made a mistake. So when you have a router, let's take the example that you have one client, one router, and one server. What you need to remember is that the network is just like the other network protocol. It's based on different layers, like the OSI model. And for the top layer, we have the module PTLRPC, which is handling RPCs, so RPCs for remote procedure calls. Physically, those RPCs are not going directly from a peer to the other. They will first get pushed to the lower layer, which will then handle splitting the data to be transmitted physically. Each layer has its own grain size, so the PTLRPC is able to send up to 16 megabytes of data per RPC. The LNet layer is able to send up to 1 megabyte. And then, so in this example, I will talk about InfiniBand, but of course, it is dependent on which network you will use, as you can have the GNI, LND, or TCP LND. And in the case of InfiniBand, the packets are at most 4 kilobytes. In the same manner, each layer also has its own timeouts, or a set of timeouts. The RPC level has the set of adaptive timeouts. You also get the pinger eviter in this. The LNet layer gets the LNet transaction timeout parameter. And you also get, in the case of using routers, the router ping timeout. I will go more in details about this later. And the InfiniBand network itself also has a timeout on the life of packets, which is defined in OpenSM by the subnet timeout parameter. You also have something which defines kind of parallelism in the different layers. So at the RPC level, you will get max RPCs in-flight RPCs to each target on your file system. At the LNet layer, you get credits, which is the global parameter, and then peer credits, which defines number of messages that can be sent between two peers. I didn't look for the IB level, but we don't really need it. So let's take the example that we want to send a 4 megabyte bulk write RPC from a client to a server for which the RPC connection is already established. And we have the LNet router in between. So an LNet router will have statically allocated buffers that can be used to store the data between the client and the server. So at first, the RPC is pushed to the LNet layer, which will handle what are called messages. The RPC in-flight counter will be incremented, so to keep track of the number of RPCs that are sent to the target we are sending to. And the LNet layer will then split this RPC into 1 megabyte messages at most. Once the LNet layer has pushed, begins to send the message, it will send it to the router. There will be an RDMA transaction which will define on which buffer the different data needs to land. And at the LNet layer, you get the peer credits counter, which gets decremented also to keep track of the number of messages which are sent. The LNet layer will then push this to the lower layer on the IB side. And the HCA will itself split the messages into 4 kilobytes messages at most. So the HCA pushes those data 4 kilobytes by 4 kilobytes to the LNet router, which will slowly fill up the different buffers. And each time you get a new message which begins to be sent, you decrement again the peer credits counter. Once you get a buffer which is complete, or one message, I would say, the router is then able to forward it to the Lustre server, and using the same mechanism, it will send it to the Lustre server. So on its side, it will again decrement the peer credits, which is between the router and the server. The same mechanism goes on and on for the different messages until you get one message complete on the server. At this time, the server will acknowledge the reception of the message to the router and continue to receive the other messages. So by acknowledging the reception of the complete message, it also returns the peer credits which was associated to it. So we can increment the peer credits on the router side. The same goes for other messages, and once the LNet router received acknowledgement for a message from the server side, it will then also send the acknowledgement to the client side, which will increment the peer credits again, and then free the buffer which was holding the message. And this goes on and on until we've processed all messages. And on the server side, once we get all messages reconstructed, the LNet layer on the server side will be able to push those to the PTR RPC layer to reconstruct an RPC, at which point we get the complete RPC back, which can be then processed. And once it is processed, the Lustre server will send another message using, again, the same mechanism in the other direction to get a reply. And at this time, the client will decrement the RPCs in flight so it can send over RPCs again. So, of course, everything here is oversimplified. There are a lot more mechanisms behind, but I thought it was useful to understand what comes after. Yeah. So, yes, in theory, we have one client, one router, one server, so everything is fine. But in practice, here is what we get. So you get thousands of clients, you get a handful of routers, and a bit more than servers in behind. So in terms of parallelisms, you can get a lot of problems. And this is why we need timeouts and credits, and to adjust those accordingly so that everything is smooth in the system. So in practice, in our first attempt, all clients were able to talk to all routers, all LNet routers, and in this configuration, we got frequent occurrences of the following messages. So you essentially get timeouts on the RDMA level, and then you get other messages, you get client evictions, dirty page discards, IO errors, ultimately on the applications, which obviously is not what we expect. The first analysis of this problem was that as we get all clients being able to use all their credits to each router, if you make the count, that means that you can get up to 1.8 terabytes in transit, which obviously is quite difficult to pass in 50 seconds, which is the default transaction timeout at the NNet level. That would mean you have to reach at least 36 gigabytes per second to have everything go on without timeout. And with HDD-based file system, for example, or if the pattern is not optimal, then it's very difficult to reach this. So the first mitigation that we put in place was to reduce this by assigning 6 routers at most for each client. So we did this by saying, okay, we have 5 islets per cluster. So each islet is 384 clients. And we dedicate 6 routers to those set of clients. That means that we reduced by 5 the quantity of data that can be in transit at any one time. And it means we reduce the performance that we need to reach to get everything passed in the 50 seconds window. So everything seems to be fine at this point, but well. So this is the configuration that we would reach. But actually, this is not good enough. We still get some troubles from time to time, even if it's much better. So we began to play with the different timeouts, but each time we were playing with one parameter, there would be another trouble coming on the other end. So we settled and said, okay, we need to understand what are the dependencies between the different parameters, and so let's think about it. So in the different parameters, we have first the peer credits. So as I said, this is the number of messages that you can send from a peer to another peer. So it was set to 32. I guess it was, this is the value that was already set when we began. I guess we kept it because we thought it would probably lower the single node performance if we would lower it. Then comes the credits parameters. So this is the same, but this is global, which means that you can't go beyond this value, even if you have more peers that you can address. So in the SMWF case, we set this to the number of routers multiplied by the number of, I think it was, multiplied by the number of storage fabrics, because we have 6 routers for each storage fabric actually. So this is 12 in total for each client, and multiplied this by the number of peer credits. So that means you can address for up to 384 messages at once for any single client. On the routers, it's a bit different because you need to be able to address all clients and servers at once. So you multiply essentially by the number of facing peers, which in our case is the 384 clients multiplied by 4 because we have 4 complexes. Plus the 138 servers on the other end. So we rounded the value to, let's say, 64K, just because we could. Then comes the number of buffers that you want to allocate. So the buffers, as I said, are at most 1 megabyte. You have different sizes. You have tiny, small, and large. The large is 1 megabyte. The small is actually 1 page. And the tiny is actually only a few bytes, so you don't really bother making them quite large in quantity, I mean. So ideally, you want also to be able to store all the messages which come from all facing peers. So in the case of the routers, these are the number of clients plus the number of servers multiplied by the number of peer credits for each of them. In our case, this means we need to have 64 gigabytes of RAM because with 64,000 of at most 1 megabyte messages, you get 64 gigabytes of RAM. So this is something you need to take into account when you're doing the architecture to size the RAM on the routers. Then comes the timeouts. So as I said, on the lowest layers for IB, you have the subnet timeout, which is by default 18, and so that's actually 4 microseconds to multiply by 2 to the power of 18, which is about 1 second. And so at some time we found that there was 7 retransmissions after this was dropped, but I didn't find the reference for this presentation. So if any one of you have a reference on this, well, you're welcome to tell it. Then comes the transaction timeout. So this one defines the yes, you have the transaction timeout and the LNet retry count. So these ones both define the timeout and the number of retransmission for a single message. And in the code, you can see that the retransmission happens actually every LNet transaction timeout minus 1 divided by LNet retry count plus 1. So in our case, and you probably want the retransmission to be after the IB lower level timeout. And so as each message transmission is sent on a different router in a round-robin fashion, we decided that we wanted to have a retry, enough retries to, let's say, try different routers in case one router was down, so that we can successfully send the message. So we set 61 and 5, which means we can have 6 attempts and every 10 seconds. Then comes the live router check interval. So this is when this defines when you want to check that a router is still alive, after which the number of seconds you want to wait. The router ping timeout defines how much time you wait once you want to check for the router to decide whether it is still alive or down. And then and the live router check interval plus the ping timeout needs to be kept below the return, well, a part of the timeout of the LNet. In our case, we wanted it to be to have the opportunity to resend it before an IB packet is dropped. So we set both to 30 and 15. The dead router check interval is the same as one live router is the same as live router check interval, except that it is triggered when the router is considered already done. Then comes the adaptive timeout. So I will try to be quick. In short, it means the adaptive timeout works so that the server is able to notify the client a bit before the deadline of an RPC that it needs more time to be processed. So it will send what is called an early reply and saying it that, okay, please extend the timeout by a certain value, which is, in this case, 80 extra. And it will repeat this process until the RPC is either processed or that we reach the 80 max value. And so in our case, we set 80 min to 75 seconds. So we need this to be higher than the LNet transaction timeout, so that the lower layer already timed out before. Then you have the early margin that you want to be high enough so that you can have several retries at the lower at the lower layer. Then comes the AT extra, which we've set to 2 times the early margin so that you don't retry, notify again the clients too often. And then the AT max is the default of 10 minutes. So that's about it for the talk. So this results in a kind of dependencies of the different parameters between them. So, well, we can discuss it if you want. Just a few credits. I wanted to thank Alexandre Louvet, who supported this work and is always supportive in our team. And also ECMWF team, who allowed me to give concrete examples.
Thank you, Sebastian.
Okay, that's it.
Any questions? Nobody?
So with all those tunings now, if you lose a router, it's quite transparent, or still you have like some file system that hang from the clients?
We can, well, the installation is now quite resilient. However, in the case of routers, if we lose really the router, there are still some few things that we didn't really clarify, but which are not the fact of the different timeouts. So, yeah, we're quite, we are happy with this setup because it changed from one day to the other completely the stability of the file system.
Okay, so and from the application point of view, if you have an issue somewhere, usually like the application crash or just hang and then recover?
Usually, yes.
Yeah.
If there are no other facts like the IB network, which has some other troubles, yeah.
Thank you. Any question? Thank you. I have to be quiet. I am sorry. I have some question, but we have our talk after you, and I can't tease. Sorry for you.
Okay.
Perhaps after, Sebastian. Thank you. So it's time for the last break. We can start at 3:35. Okay, guys, take your seats. It's the last presentation from the lab. It's time. Time is over. Okay, thank you.
All right, so our last presentation will be done by Gabriel Delbarry and Aurélien Séden. Gael has been working at CEA for 14 years in the HPC division. During the first 7 years, he was a system administrator in Linux Windows environment. In 2015, he joined the HPC storage team as a software administrator. And for the last 5 years, he has been in charge of the next storage architecture for supercomputers, research and development on HPC storage platforms, and L3 system support on storage clusters. And Aurélien has been working at CEA for 12 years in the HPC division. During the first 11 years, he was an HPC system administrator. End of 2021, he joined the HPC storage team as a storage administrator and works on storage optimization and debugging. He also is in charge of the in-house Linux distribution at CEA, Océan.
Thank you, Guillaume. It's again me, sorry. So we are going to talk about the talking of Lustre file system at scale around 20,000 of clients. We haven't synced with Sebastian Peszczerski, but it's a continuation of its presentation. In this presentation, you will have the impact when you don't set the right tuning, with the S tunings. The agenda is we will do a quick seat update, and after that, we will explain the context case study and the different parts where we did some tunings. It's like a horse riding race, if I can say. I don't know if it's a good sentence, but you try to think something, so it's fixed, but like Sebastian said, you have another issue after that. So yeah, it's a life. Anyway, a quick seat update. At CEA, we have still 2 production compute centers, one for defense and one for European research. We have also one other, which is the compute center of R&D, which is pretty useful when we want to test, to bench hardware and software stack. Some numbers about the compute power we have on the defense center. We are about 40 petaflops and we have 20,000 clients. But they share the same storage approach with a similar design. In fact, it's the same architecture. Why? Because it is the same team, of course, so it's easy to administrate, to manage. And also it's for a user perspective. You see, it's a pretty old picture here. It was done by Stefan, so it's pretty old, but it's still true today. The name of supercomputers have evolved. We have many, but it's still true. We have a data-centric approach where we put the storage at the middle place. Okay. Now we are running Lustre 2.12.9++, of course, with a Lustre HSM version. We plan to upgrade to 2.15 in Q2 or Q3 next year. Some numbers, you have some numbers in throughput, which is not pretty interesting here because anybody can do some high numbers. You can do this number with HDD drive or SSD. It's just a question of numbers. But at CEA, we have recently IOPS workload and requirements. As you know, on the defense parts, we have a Lustre file system in random writes around 20,000 millions of IOPS. So, I am sorry, we go back to past. Last year, Q3, Q4 2021, we had a new supercomputer, which code name is Exa one, a big one. But of course, this node would like to mount our Lustre HSM file system. These new supercomputers come from a new interconnect, the Atos Big Psi, with a custom LND, a specific LND. To connect the compute nodes to the servers, Lustre servers, we have 60 routers. So it adds 7,000 of clients plus the current we add. A quick picture of what we have. You have on the left the last current situation where we have 12,000 of nodes which mount the Lustre file system interconnected by 200 LNet routers. On the server side, we have 4 metadata servers and 40 OSS. But on one OSS, we have many targeted for a total of 384 OSTs. Again, on the right, you have our new supercomputers. I would like to mount this file system. To do that, it goes through 60 LNet routers. Okay, what we know, we have 20,000 clients in total. Have you seen 3 supercomputers with the same Lustre FS? So we have to be careful, because if we have an issue of one file system, all of these supercomputers are hung. Okay, we have heterogeneous router configuration due to the kind of interconnection we have. We have Big Psi V1, Big Psi V2, Connect IB, Connect X4, Connect X6. Also, we have Lustre servers with HA configuration. These servers are all virtual machines. Okay, what we know. Lustre is scaled pretty well, up to 10,000 of clients. If you follow the Lustre manual, you can have a well file system. But we have seen that a long time ago, in 2012, created some issues with large supercomputers. It's an excellent paper which explains how the OBDPing is working. Okay, we will see what is it after. The last point is the new interconnect is pretty young. In fact, at CA, we have the luck to test the new interconnect. So we had some issues on large scale. Right now, it is fixed. So, gave us a try to mount the FS. All the production is working. Okay, it's not true. We are in a maintenance slot, but anyway. What we do is to mount all nodes at the same time. Okay, the result was pretty cool. We have seen many target disconnection on already mounted client. But what we can say, we could mount it successfully the FS, but in step of 500 clients. Okay. But we need to understand what is going on when we do this and why we cannot mount as soon as clients. What we have seen during this, it's time, we have seen many LNet credit starvation on routers and servers. We have the memory which increased by 50%, which is pretty huge. And we've seen many small RPC on the MDS NGS node, about 180,000 RPC per second. A quick sum up, but you have seen on the Sebastian talk, it's just when you are working in Lustre, you have to know exactly in which layer you are working and you are rely on. On this topic, we will talk about LNet, the point-to-point communication between client and router, between router and server, and of course also with PTL RPC, which is an end-to-end communication protocol from client to server. On the left, there is the picture which is extracted from LAD 15 from Chris talk. This talk was amazing and pretty useful when you want to understand how credit are working in Lustre. So, first analysis. What we can think is that, in fact, we have not enough resources on server side to absorb the client activity. You can monitor this easily. Sorry, James, it's the big face. With the syskernel debug and net peers. What you see here, you have the line in bold. You have to highlight the bold value and the mean. The mean value is the low water mark. So sometimes, perhaps in your configuration, in your system, you will see some minus value, but it needs interpretation and analysis to understand why it's low. What I want to say is that it's not because you have a minus value, it means that you have an issue, okay? But when you see the last column, the Q column, it means that you enqueue messages. In this kind, when you have this both value and the low watermark have 5 digits, it means something goes wrong. Okay, so first approach, of course, we have not enough credit to absorb the amount request. Just to sum up, you have understood when you are doing LDMR communication, you write some information on the remote memory of one node. You don't care, you don't know if you lose a packet and so on. So you have to rely on something, on a protocol. In LNet, the credits is the throttling mechanism. It's like, for people which know TCP, like TCP congestion windows and the algorithm they are relating with the kind of mechanism. A quick notice, you have understood in the presentation of Sébastien, peer credits is different from credits. And what we can sum up about the peer credits, it's a max in-flight and net messages allowed for a peer. And there is a difference with the RPC, max RPC in-flight, okay? We are not on the same layers. Okay, what we have done at CA is that we adjust the higher value of credits we could achieve with some restriction. We are limited on the MOFET version. We are stuck on the 4.7.3 version because we have Connect IB cards. And this version of MOFET plus some Connectix firmware version, we are not able to go through 42. Okay, there is an exception on the client side where we couldn't increase the value of credit above 32. There is an LND limitation. Okay, about the credits, the default is 256. It's the same rule of thumb Sébastien presents. We compute the credits, the value is peer credits, by the number of peer you've seen on the LNet layer. A quick remark, if you want to check how many credits you have, the value is divided by CPT. Okay, we are going to see what is a CPT after that, but be careful in the code, there is a minimum value of 64 credits per CPT. Okay, you have understood that you have to compute the number of credits on the routers, thanks to Sébastien, but we did another thing, we did some trial, and we monitor the credit consumption during worst case we have in the compute centers, and we just set up the right value on the router. Okay, it was pretty cool with this kind of modification. We can parallel mount the 7,000 clients successfully, but we have seen some disconnection on some parts, some clients. We have still few credit salvation, but we are not on 5 digits, only 3 digits, which is not a huge value. And good news, other clusters are fine. Okay. It was amazing, but after this modification, we had a kind of job which breaks 2,000 nodes. That was a job issue. But the impact of this is that we have a kind of storm, the baby storm, remember, of big size interconnect instability, where some clients are able to communicate, but not. After some piece of time, a bit, I'm talking not in netlet, and I am on the layer of the network communication. So the result is we have out of memory on routers and servers, and other computers are stuck. So it's a bit catastrophic issue. And when we monitor the number of messages we have between routers and servers, we are close to 8 million of RPC per second. How can we handle this? I think Aurélien is going to answer to this question.
So yes, to handle this issue with the 8 million of RPC per second, the first approach was to understand why we cannot digest or absorb this amount of RPC. So we are first looking for the CPU partition table, which is the CPT, just like Gaël said before. So to monitor that and to try to reproduce this, we use the LNet self-test tools, which is a good tool to try that. And we see a limitation on IB servers and routers about 180 K RPC per second. So there is an issue here with a suboptimal CPU load distribution because some of them are about 90% of usage and some others just about 30%. So with digging this issue, we hit the LU14676, which is about the hashing function between two peers in the LNet protocol. So given that, the idea is to adjust and to have a better number of CPU partition tables to handle the more and more requests. So here you have the configuration we put in production at CEA with a CPU configuration of 12 cores and 1 NUMA node. As you can see, we just use 11 of CPUs and we let one for the system. So with this configuration, we add a big boost, so like by 10 RPC absorption per server. So it's a good news. But we still have many RPC on MDS and MGS during the term of connection, during the mount process of the 20K nodes. So we add some clues. So first of all, we want to analyze the difference of the MGS and the MDS traffic. So we separate the both and have a better analysis of this situation. So we can monitor these two traffic and show what is going on this different connection. So we can monitor the different CPU partition configuration by the two ways. The first is the LNetCTL netshow-v, which will use like a client or the tool itself, and we have the direct access to the CPU partition table in the syskernel debug LNet file. So by increasing the CPU partition table, the trade-off is that we gain memory usage on each server, which can lead some problems. So we still have we absorb now a lot of RPC, but why have we this RPC? Because it's really a lot of little message which cause our root problem. So we still want to know what is going on. So what we didn't say before, yes, we did that. The job produced some out of memory on our servers. So with our tuning, we just have a little one out of memory exception on some server in some cases. So we still continue to analyze this, and we try to understand the RPC storms. What we analyze is that we just have high priority RPC. It's just this storm of high priority RPC which leads to the out of memory on our servers. So when have we the high priority RPC? Most of the most common case, and with an unstable network, we have the overlapping process, which is the main RPC we've seen. The overlapping process will have a different function. One is to have health status for the server to the client and to the client for the server in the both ways. Overlapping are regularly sent like a keep alive status to know if a server is alive, to know if a client is alive. And really regularly, and at the scale of 20K nodes, it goes a lot. It can be a lot of traffic. And another high priority and overlapping process can be sent is when a client has no more connection, or no more credit, or has a network trouble. He'll try to resend immediately the connection, and so on and so on. So with the number of clients, it's really a huge traffic which leads to a net floodings with RPC, with overlapping and HP RPC network packets. So we profile, to understand why we have this deconnection, we profile the user workload. So it's a quite big workload with an IOR, with one file per process, with 1K nodes. So multiplied by the number of process, it's really a big workload, which is not really, it's hard to absorb, let's say. And what we can say is that because of that, the OST-IO service on the servers, on the OST, was the one who leads to the out of memory. So we have two solutions two ways to fix this. Is first to try to fix something in the user code, and the other one is to reduce the overlapping burst, which is what we said before. So the solution is to use adaptive timeout, and that's a way that Sébastien talked just before. What we are sure is that because of the network issue and reconnection, the storm comes from that. Just without doing anything on the file system, we can have this kind of behavior. So for RPC timeout, Lustre relies on adaptive timeout, and the best practice talk about AT max, but not often of AT min, which is the one we choose to address this issue. So Sébastien talked about that, but globally, a value of 0 for AT min means for the client, I want to resend immediately a packet which was not sent, and this is why we have this storm. So tuning this value to a good value will solve our problem, in fact. So relying on our LNet configuration, we can compute the good value of the AT-min parameters, and this will say to the client, just wait, I know this, you cannot send your packet, but wait just a few seconds, and if you retry after that, maybe everything will go back better. So that's what we compute. So AT-min is the retry count +1 by the transaction timeout plus a little piece of processing time. So at CA, we choose to set up AT-min to 55, which solve, in fact, the storm. So to conclude and to sum up this presentation, we go deeper on this problem, and we simulated 80K parallel months on client to see if this kind of configuration can be robust over the time. And so what we can say is that it takes 30 seconds to mount. Some credit starvation, we can observe some credit starvations, but everything goes well, in fact. We don't have any out of memory, and everything is quite stable. On our production, the 20K clients are successfully mounted and are used in production. The bad behavior of our user can be stopped, so no more OM on our production. On our production. Now, luckily, we have a new BXI version, which are a lot more stable now. So everything goes very well now. So yes, what we don't say before is that we had the out of memory was produced by some calls like the PTLRPC GROW rect buffers, which was a function which allocates the memory, and this is the deep inside of the OM. We also have some TBF configuration to limit bad user request and workload. And so to conclude, we have to have a large cluster and stable file system, we need to tune correctly the LNet credits, to have a good CPT configuration to absorb most of the traffic, and a good adaptive timeout will help if there is some network issues. Thank you. If you have questions.
Thank you, Aurélien and Gaël. Any question for Aurélien and Gaël? With these two last talks, you have everything to tune. Yes, Andres.
So the AT-min, being too small, I mean, that's something we've seen at a few sites, but, haven't had time to work on. There is an open ticket. I don't know if you have any interest, to what we would, I've been thinking is having, because the server is the only one that knows, how many clients are connected. Each of the clients don't know that, but AT-min is important on the clients, and have some, mechanism for the servers to, say, oh, as the number of mounted clients increase, please increase the AT-min. And it doesn't have to be instantaneous because, you don't need it right away, but if the clients are pinging, if they would get some update, right, that says, or through adaptive timeouts that say, increase your AT-min, because on a 20,000, client cluster, you have to be more tolerant than, we also have to work in, the 20 client kind of financial or whatever, where they don't want to wait a minute for it to even try to recover an RPC, right? And so I don't know if that's something you'd be interested to work on?
Yeah, I think so. Andreas, is it the ticket from Patrick? Yeah. Okay. Okay.
Another question? Yeah, thank you, Gaël, Aurélien.
Thank you.
So voila, Lab 22 is over. First, I would like to thank Météo France, for which it was one of the first participation. But at the beginning of the conference, the forecast was something like 2 days full of rain. So thank you for fixing that. Now the weather is quite sunny, and you will see. Thank you all for coming to LAD, for going through the pandemics, the climate disasters, risk of nuclear wars, also for experimenting jet lag, construction work in the public transportations of Paris to prepare Olympic Games for 2024. So thank you for going through all of this and coming here to meet together. It was great to see you all after 2 years and a half of virtual meetings. It was so good to just go and see someone and ask how is your Luster5 system without having to do a doodle, schedule a call, and talk virtually. So it was being very good. I would like to thank sponsors, of course, who made it possible to overcome the inflation of renting such a meeting room, which is actual. Thank you, of course, to the speakers who spent time preparing presentation, figures. It's a lot of time, so and it was at the end a very valuable content. So I would like to thank them all. Of course, I would like to thank people who organized it. Ludovic, who managed the broadcast on YouTube for those who could not do the trip. Of course, Gaël for running the conference and for introductions, Guillaume for introducing, and of course, all those who organized or who managed the room, the social event, all of this. So we have distributed a link to a survey. Please answer for encouraging us preparing the next slide. So as Gaël said, LAD is now 10 years old. So I wish the best for the next 10 years. 10 years ago, we must be talking about petascale, something like that. Now we are in the exascale area. Where will we be in 10 years? Perhaps we'll talk about zetascale. So I wish Luster will handle this. In the next 10 years, we'll have many challenges to face with in the next 10 years. So long life to Luster, long life to LAD, and see you next year. Thank you all. Have a nice trip back. Thank you. If you have a few minutes, I suggest we have a group picture here on the scene. You can take your cap you had if you took it with you. Thank you.